Welcome to IT.Solution, your total network, system, firewall, and security partner.
Let's dive right into this explainer. Today, we're bringing some serious energy to CCNA SRWE Module 2. We're going to track a single Ethernet frame through the dynamic, digital mailroom that is a local area network switch. If you're gearing up for your CCNA 200-301 certification, mastering this module is absolutely essential. We're going to break down the exact step-by-step logic these incredible devices use to keep your modern networks running so smoothly. So let's start with a massive question. How do these devices manage to tame the absolute chaos of network traffic at such blinding speeds? I mean, consider that even a low-end switch has multiple ports, and with the minimum size of an Ethernet frame, these devices have to make millions, literally millions, of forwarding decisions every single second. They pull this off using specialized hardware called ASICs, or application-specific integrated circuits, to process everything almost instantly. But here's the thing. The hardware is really only as good as the logic driving it. Okay, here's our roadmap for today. We're looking at the role of a switch, building the MAC table, making forwarding decisions, switch forwarding methods, and finally, collision and broadcast domains. Let's kick things off with Section 1, the role of a switch as the digital mailroom. Ultimately, a switch really only has one primary job, and that's to forward frames to the correct destination MAC address completely loop-free. It does this using the MAC address table, sometimes called the CAM table, which acts as the switch's highly dynamic address book. But here's the real catch. When you first take a brand new Cisco switch out of the box and power it on, this table is completely empty. It doesn't know where a single device lives. Moving on to Section 2, building the MAC table and linking those addresses. Right, so if the address book starts out totally blank, how in the world does it learn where everyone is? Well, it relies on a very elegant two-step process. Step 1, the switch learns. Every single frame that enters a switch gets inspected. The switch acts exactly like a mailroom clerk, checking the incoming frame's return address, that's the source MAC address, and noting the exact port number it arrived on. If that specific address isn't already in the table, it gets added right then and there. Then comes Step 2, forwarding. The switch checks the delivery address, the destination MAC, to figure out how to route the package. And this brilliantly illustrates just how highly efficient and dynamic this memory actually is. Get this, if a device stops talking, its entry ages out after just 5 minutes, or 300 seconds. Gone. Now, if the device sends another frame before that timer is up, the switch refreshes the clock back to 5 minutes. This constant flushing out of inactive addresses saves extremely valuable memory space and guarantees the switch is never working with outdated network paths. Okay, Section 3, making the forwarding decision or actually delivering the package. So, once that memory table is populated, it's time to actually make the forwarding decision. Let's break down the logic here because it's absolutely crucial. If the destination MAC address is already in the table, we call that a known unicast. The switch just makes a direct point-to-point delivery out of that specific port. Simple, right? But what if the address isn't in the table yet? Well, that's an unknown unicast. To guarantee the package reaches its target, the switch floods the frame out of every single port, except the ingress port, the one it just came from. And you know what? It does the exact same flooding action for broadcast and multicast frames. This ensures the data gets exactly where it needs to go without accidentally sending it backward into a massive loop. Let's jump to Section 4, switch forwarding methods, where we look at speed versus accuracy. All of this logic builds directly into the hardware choices, happening instantly inside those ASICs we mentioned earlier. And here, we really see a stark contrast between two primary forwarding methods. On one hand, you have store and forward, which provides meticulous error checking, but naturally takes a little longer. On the other hand, cut-through switching provides rapid-fire delivery, dropping latency to incredibly low levels. The trade-off? You run the risk of accidentally passing along corrupt data because, well, it simply doesn't check for errors. Let's look a bit closer. Store and forward patiently buffers the entire frame. This is actually Cisco's preferred switching method. By holding the whole frame, it can perform a mathematical check against the frame check sequence, or FCS, at the very tail end of the frame to check for CRC errors. It effectively destroys corrupt frames, along with undersized frames, which we call runs, and oversized frames, known as giants, before they can spread and eat up all your bandwidth. This method is literally required for quality of service on converged networks. Think about when you need to prioritize voice over IP traffic. You absolutely need store and forward. Conversely, you have this brilliant cut-through method. It reads just the first 6 bytes of the frame, just enough to grab the destination MAC address, and immediately fires the data out the egress door. It is perfectly designed for environments that need latency to be under 10 microseconds. However, because it skips the FCS check entirely, it will gladly forward a corrupt frame. Now, there is a compromise method called fragment-free switching, which checks just the first 64 bytes to eliminate early collisions, but standard cut-through, that is all about pure speed over safety. Moving on to our final topic, Section 5, collision and broadcast domains and how we structure the LAN. Let's zoom out to the macro-level network design and see why all these micro decisions actually matter to the overall health of your network. Understanding domains is absolutely critical here. Back in the days of old Ethernet hubs, everyone shared one giant collision domain, which was a total nightmare for performance. Switches completely fixed this by placing every single port into its own isolated collision domain. Even better, if a switch is running a full duplex link, it essentially turns off the old contention rules and completely eliminates collisions entirely. It's a game changer. However, while switches kill collisions, they do absolutely nothing to stop broadcasts. By default, a switch will flood a broadcast frame out of all other ports, meaning it actually extends the broadcast domain. As you can see, connecting multiple switches together provides massive port density, which is awesome for scaling up the LAN. But you've got to remember that all those devices still share one giant, noisy broadcast domain. Think of it this way. If one PC shouts, every single other PC hears it. Too many broadcasts will inevitably cause congestion and really poor network performance. The only way to break up this massive broadcast domain is to introduce a Layer 3 device, like a router. And that brings us right to the very edge of the local area network, leaving you with a pretty big question. If Layer 2 switches are the undisputed kings of local delivery and microsegmentation, who takes the package across the internet? How does a router actually make its forwarding decisions compared to a switch? Keep that provocative thought in mind as you continue your CCNA studies, because honestly, mastering the switch is only the beginning of the journey.
Thank you for watching. See you in the next episode.